You know that simple story we're all taught about how AI learns? The one with the nice smooth curve? Well, today, we're going to tear that page out of the textbook. We're diving deep into the weird, messy, and frankly, kind of chaotic reality of how these things actually get smart. All right, so let's jump right into the heart of the mystery. To really wrap our heads around this, we have to look at this super weird thing that some researchers at Stanford stumbled upon while they were training these massive neural networks. Okay, so this graph right here, this is the whole puzzle in one picture. That blue line, that's the training loss. You can just think of it as the model's error score. See how it's going down? That's good. It means the model's getting smarter, making fewer mistakes. But whoa, look at that orange line. Whoa. That's a measure of how unstable the training is. It just shoots up and then hangs out right on the edge of complete chaos. So get this. The model is improving while the process of teaching it is about to fly off a cliff. How is that possible? That's the big question. And this is a huge puzzle, right? Because everything we thought we knew about optimization says this shouldn't be happening. If your training is this unstable, it should either just explode or, not learn anything at all. It shouldn't be getting better. So what is going on? To really get why this is so mind-bending, we've got to take a quick step back and look at the classic textbook picture of optimization. It's all about one simple idea: making a map of a super complicated place. And the main tool we use for this map making is something called a Taylor expansion. Now, don't worry about the name. Just imagine you're a hiker lost in a massive, foggy mountain range. That whole mountain range is your AI's problem, the loss function. A Taylor expansion is like a magic tool that lets you create a simple little map of just the ground right under your feet, using only two things: how steep it is and how it curves. So with this little map, you basically have two ways to find the bottom of the valley. On one hand, you've got gradient descent. This is the super simple way. It only uses the slope. It's literally like looking down at your toes and taking one step in whatever direction is steepest downhill. That's it. But then you've got Newton's method. This one's way smarter. It uses the curvature, the second piece of information, to sketch out the entire shape of the little valley you're in, a perfect parabola, and then it just jumps straight to the bottom. Way more efficient, right? So the big point here is that the standard way we're taught to think about this is like finding the bottom of a nice, simple, perfectly smooth bowl, a parabola. In this perfect little world, you either slide gently down to the bottom or you take too big of a step and you just fly right out of the bowl. No middle ground. Super clean, super simple. But as we just saw with that edge of stability thing, reality is not clean and simple. It's messy. The real world isn't a perfect bowl. And that means our perfect little map, it's wrong. So let's see exactly where it all falls apart. And this just shows it perfectly. On the left, there's our theory, the simple parabola. On the right, that's what really happens in the wild. Each of those colored lines is the path an optimizer takes. The only difference between them is the learning rate, basically how big of a step it takes each time. And look, they don't just get to the bottom faster or slower, they go off in completely different directions. Our simple little parabola map has no way to explain that. And the researchers who found this, they don't mince words. They say it right in their paper. This cannot be explained by a quadratic approximation of the loss. In other words, the map is wrong, period. Okay, so if the landscape isn't a simple bowl, what in the world does it actually look like? Well, the team at Stanford managed to visualize it, and what they found was a hidden structure that's way, way more interesting. First thing they found, when you get really close to the bottom, the valley walls are way flatter than a parabola's. They have a name for it: subquadratic growth. And this flatness is the secret sauce behind the edge of stability. It's like a built-in safety net. It lets the optimizer take these huge, crazy, unstable steps without totally flying out of the valley. It cushions the fall. But then, when you zoom out, you see the second piece of the puzzle, something they call separate scales. Turns out it's not just one valley at all. It's more like these tiny, sharp, narrow canyons that are hidden inside of massive, wide-open basins. Think canyons inside of a Grand Canyon. It's this incredibly rugged, multi-layered landscape. So you put these two things together, that flatness at the bottom and these nested canyons, and what you get is what the researchers call a multi-scale structure. This is our new map. This is the truth. It's not a simple bowl. It's a complex, rugged, and honestly incredible landscape. Okay, great. So we've got a new, better map of this crazy terrain. But so what? Why should you care? How does knowing this actually help us build better AI in the real world? Well, here's why it matters.
Because some of the absolute titans of machine learning, I'm talking about algorithms like XGBoost that win competitions all the time, they don't just follow the simple slope. Nope, they lean hard into that more complex second-order map. They use the parabola.
And the reason XGBoost is such a beast is because it uses this more complex map. Here's the game plan. It starts with a basic guess, then, and this is the key, it creates that local parabolic map. Based on that map, it builds a brand new little model whose only job is to fix the worst mistakes. Then it adds that new little guy to the team and does the whole thing again, and again, and again. It's constantly redrawing its map at every step, which lets it navigate this incredibly complex landscape like a pro. So here's the bottom line. That old, simple map of a perfect ball, it was a nice starting point, but it was just incomplete. It couldn't explain all the weird, powerful stuff we're seeing in modern AI. But now, by understanding this true multi-scale landscape, we can finally get why an optimizer can dance on the edge of chaos and still learn, and why something like XGBoost is just so darn good. It's simple, really. A better map lets you build better explorers. So, while this new understanding solves our big mystery, it also just blows the doors open to a ton of new questions, doesn't it? We are literally just beginning to draw the edges of this map. You have to wonder, what other weird secrets, what other hidden structures, and what revolutionary new tools are still out there, just waiting for us to find them in this wild mathematical world?